So my name is John, in case you've never met me. I actually recognize some of you. I TA'd for some of you before. But I'm currently a master's student at UCLA. I also was an undergrad once upon a time here as well, right before, and was president of ACM AI. So it's great to be back. So yeah, today is the first day, first week for our reading group this quarter. So just for those of you unfamiliar, we're going to be kind of going over more advanced topics in machine learning research beyond what you might see in our beginner and advanced tracks. And the goal here is to kind of give you some exposure into looking at more cutting edge research that's going on in the field of AI and machine learning that's going really, really fast. So yeah, that's what we'll hopefully be doing this entire quarter. So yeah, for those of you who just came in, this is the first session for our reading group. Today we'll be going over an introduction to reinforcement learning. And again, this stuff might get pretty complicated. So feel free to stop me and ask questions at any time, or if you want to just chat about anything, feel free to just shout it out, raise your hand, whatever you want to do. Cool. All right, so a quick overview of what we're going to go over today. So just some motivation behind why we even care about reinforcement learning at all. And then we'll talk a little bit about some problem formulation, then some algorithms, how reinforcement learning is deployed in various products now, and some open challenges and future work. Okay, so first, some motivation. So what's missing with our current AI? Well, as many of you know, most of our current AI systems are based on supervised learning. However, when we're making decisions about what we're trying to do in the real world, we're often actually making sequential decision-making problems. So for instance, we've seen that we can do object detection with deep neural networks. However, we don't usually just care about the object detection in and of itself. We want to use this object detection to make some series of decisions that might affect the real world. So for instance, we might use this object detection to make decisions about steering and acceleration in some self-driving car. For recommendation systems, we can recommend movies or content to people on their social media feeds. But what we really want to do is we want to be able to, show, various sequences of items that keep, various metrics we care about really high, like engagement, or to keep them, on your social media platform, or keep watching movies, or keep, subscribing to Netflix or whatever it is. For generative AI, oftentimes we're generating things that were being used to send to people. Maybe you're using AI to actually, send text in your email. This might be a back and forth, long-term sequential decision-making thing. And the problem here is that most of our systems, supervised learning is not directly optimizing for this end goal. We're just looking at some piece of data one time, and then we're outputting some classification, some prediction. And it's not usually, in the end, in and of itself, what we actually care about. And it turns out that you can actually formulate every single problem as a reinforcement learning problem. And RL is really the most general way to formulate any kind of problem we actually want to solve. And so if you look at anything like any task in supervised learning like object classification, we can think of that as a single time step decision-making problem. So what exactly is reinforcement learning? RL provides a mathematical formalism for learning-based decision-making. So typically in a RL setting, we have some kind of agent like this robot here, and it's making some decisions in some environment in the world, and the world is sending back some consequences for those actions that that agent is taking in the form of observations. So what it sees, how the state of the environment changes, and then rewards, some kind of measurement of how good you're doing some task. So to give some more concrete examples of what this formalism might look like, for instance, if you're training a dog to do some tricks, the actions that this dog might do might be some kind of muscle contractions. And the observations that the dog has might be the sight, smell, and other commands that you give to the dog. And the rewards you might, the dog might receive are food or other kinds of treats from the owner. For something like a robot, the action space might be something like the motor torques that are applied to move the joints of the robot in order to do some specific tasks. The observation space here might be some camera images or other sensor input that's on the robot. And the rewards might be some measure of task success, like whether it's able to pick up some object that you want the robot to pick up. There's also other examples that might not be super obvious where you might apply this reinforcement learning paradigm. So for instance, in inventory management. In this setting, maybe your actions are what you want to purchase. Maybe you're, Amazon, you want to figure out how many, items you should purchase of a specific item so that you match the actual demand that you have on your platform. And your observation might here be like things like inventory level, how much your customers are purchasing, and your rewards might be how much money you're actually making. So how much money you're spending minus all the costs that you're spending money to stock items and shipping and doing all that sort of stuff. So how is reinforcement learning different from standard machine learning? And it's often a lot more subtle than you might think. So in supervised learning, you're typically given some data set D, and you have some inputs X, and you're trying to regress or classify some output Y. This data set is typically fixed before training. However, in the reinforcement learning setting, you often need to collect additional data during training, and maybe you don't even start off with any data set at all. And this means that your data set actually changes throughout training, which is a really difficult problem in and of itself. Like imagine if you're trying to train some object classification, but every time you took a gradient step, your data set actually changed. That's actually the problem that we deal with in reinforcement learning. That makes training a lot more unstable, and we have to do a lot of different things in order to account for that. Another thing is that a lot of usual assumptions that we make inside supervised learning do not any longer apply to reinforcement learning, which actually breaks a lot of theory and things that make deep learning and supervised learning really easy and successful. So for instance, typically in supervised learning, we assume that data is IID or independently and identically distributed. And that means every single data point we assume to be coming from the same distribution, and that something from one data point doesn't actually tell you any information about another data point. In the real world, this actually is rarely true, but given how deep learning works and is kind of magical in a lot of ways, to be honest, we don't have a lot of good formalisms or theory behind why it works. This assumption still ends up being okay. And another thing is that in supervised learning, the ground truth is known during training. So you know what exactly the correct answer is supposed to be. However, if you're training like a robot to perform a task from scratch, you actually don't know what the correct motor torques are ahead of time. The best you have in most cases is some kind of separate measure of how successful you are at doing that task. So, and before we get into some more mathematical formulation about reinforcement learning, I want to kind of give you some taste of where reinforcement learning has been applied in the real world already, just to give you kind of a sense of, the fact that this is not something that's just, in theory or in research, but this has real practical implications in the real world. So you've seen reinforcement learning being used to beat the world champion at Go, some grand challenge that many thought would not have happened for many, many more decades, but was able to be done with reinforcement learning. We're able to do things like robotic control, manipulating various objects with reinforcement learning. And actually, ChatGPT, arguably the most important advanced and released AI product in the past, couple years, actually reinforcement learning is the key ingredient to making that system work properly. So now we're going to kind of formalize what reinforcement looks like more mathematically. So typically in reinforcement learning, you have an agent which is running some policy pi. This policy pi is a conditional distribution over actions given state and observation. So this is what you're going to see here. So pi theta AT given OT. This is probability. So if you've taken like Math 178 or Stat 100A, this is saying that your policy is saying that when you see observation O at time step T, what is the distribution over actions you're going to take if you're following that policy pi? And this is parameterized by parameters theta. So you can represent your policy as some neural network, and the neural network weights and biases are your theta. So just to give a concrete example here, suppose you're like a human or a robot, and you're trying to, survive, out in the jungle, in the wilderness. Your observation might be, the images that you're seeing. For instance, this tiger here, and then it goes through your brain, your neural network. And then based on that, you're going to take an action. Maybe you walk to the left or right, or whatever else you might want to do. So here, observations are what the agent actually sees. However, there's usually some concept of partial observability here, which means that what the agent actually sees does not contain all the information that there is in the environment needed to act optimally. So the observation is a function of the state of the entire world. And just to give a more concrete example here, suppose we're in the same environment we were talking about before, and you're looking at this observation here. You might see that there's like a cheetah and a gazelle. However, the cheetah is partially occluded or blocked by this car here. So your observation might be the pixels of this image. But the actual state of the world, the actual information you need to act optimally is actually, for instance, the pose and orientation of all of the relevant agents in the scene. Are there any questions on this formalism? Okay. Yes.
So what exactly do you mean here by like a distribution of possible actions and things like that?
Yeah. So that's a great question. So if you see this, tiger, you might have a 0.9 probability of turning and going 180, and the rest of your actions might have a total sum of 0.1 probability mass. So this, in general, your policy is stochastic, so it's not deterministic. You can't have deterministic policies. That just means that there's some particular action where pi a of O is 1. Does that answer your question?
Yeah.
Okay. And just to give you an idea of why you might sometimes want a stochastic policy, suppose you're writing an RL agent to play like poker or some other game. You don't want to have deterministic actions. That's actually really suboptimal because it makes you really predictable. Okay. So some additional formalism for reinforcement learning. Typically, reinforcement learning is defined as a Markov decision process. And what this means is that it has the Markov property, which means that in this graph that you see here, I'll explain a little bit, each node in the graph is only dependent on its parent nodes. So in reinforcement learning, there's another probability distribution you need to be aware of, and that's the dynamics or transition probability. And so this defines some probability over next states, so states at time t plus 1, given your current state and the action you take at that state. So this tells me if I'm a robot and I see something and then I take this action, what's the distribution of next states going to look like? So maybe like if your your state is you're looking at a cheetah and your action is you walk towards the cheetah, there's a probability, the probability that the next state is you are dead is probably really high, right? That's what the transition probability tells you. And so you can kind of visualize a Markov decision process as this kind of graph here. So you have state 1, your initial state, and your observation is some function of that state. And this observation is used to define your action distribution given your policy. And both your action and the state are used to define the next state. And we just keep doing this over and over again. However, because this has a Markov decision process, Markov property, what you see is that the probability of going to, say, S3 is only dependent on S2 and A2. This is how the Markov property works because these are the only parent nodes in this graph. And so what that means is that state 2 and action 2 tell you all the information you need to define some probability distribution over state 3. Information about state 1 and action 1 do not add anything else. In other words, it's conditionally independent given the previous state in action. Next state is conditionally independent given the previous state in action. Any questions about this? Okay. One more mathematical formalism in reinforcement learning. Oftentimes, at each time step, you get some reward. And your goal in reinforcement learning is to maximize your total sum of rewards over your entire trajectory. A trajectory here is a sequence of states and actions. And basically, typically, what we want to do is we optimize for the total discounted reward. And so what this discount factor means is that at each time step, we multiply the reward we get by some value gamma between 0 and 1. And we use that, gamma to the power of t times the reward, and the sum over all of that is what we're trying to optimize. This is what we're trying to optimize here. Tau here is the trajectory. This is the sequence of states and actions that your agent takes. And the reason we want to do this is because oftentimes we want to optimize, we want to prefer reward now versus later. So suppose you can get 1 million reward at t equals 5 and 1 million reward at t equals 100,000. You're going to prefer reward 1 million at t equals 5. Yeah.
question. So, is this optimization something that's done at every step in the sequence?
Yeah, so we'll get into how we optimize this a little bit later. But typically what happens is there's multiple steps in a reinforcement learning algorithm. There's a step where you're just collecting data. So maybe your policy at the beginning is completely random. You're gonna run your robot or your agent in your environment and then see what happens, see what reward you get. And then once you already figured out what happened during all of those, what we call rollouts, then we do something with optimization to kind of change our policy. But I'll get into that a little bit later. Any other questions about this or anything else we've gone over so far? Okay. All right, so now to the actual entire goal of reinforcement learning. So like I mentioned before, we have a trajectory tau, which is a sequence of states and actions and rewards in an episode. The reward RT plus 1 will be the reward we get for taking action A at state S, AT at state ST. And given all the equations that we've looked at so far, which I admit is a lot, we can actually define a probability distribution over an entire trajectory. So P theta of tau. So this is given you're running a policy parameterized by parameters theta, what is the probability distribution over your trajectories? So your probability distribution over S1, A1, S2, A2, so on and so forth to capital T, the end of your trajectory. And it turns out we can use the Markov property and our policy to define this probability distribution exactly. So this is your probability of S1, your initial state. And because we have the Markov property, we know that P of ST plus 1 given ST AT is all you need to calculate the probability distribution of the next state. Otherwise, if we didn't have the Markov property, ST plus 1 would be dependent on every single previous state in action. But we use this Markov property, so it's just this probability distribution here. And because this is just a definition of joint probability, we just multiply all of these terms, so the transition probabilities and our policy action distributions. So this gives us the probability distribution over the entire trajectory. And what we want to do is we want to find theta star. So for instance, the parameters of our neural network policy that maximizes our total expected reward over the distribution of trajectories induced by running our policy parameterized by parameters theta. I know that was a lot of equations in math. Are there any questions? Just making sure. Okay. One more thing I should also mention is that this Markov property is true for states only, not observations, because observations don't tell you full information about what's going on in your environment. So you cannot write the same equation with observations. Yeah.
Can you go with the second equation?
This one?
Yeah.
So the goal of reinforcement learning, so you have some policy that's parameterized by parameters theta, and the goal is to find parameters, we'll call it theta star, that maximizes the expected total reward. This inside this expectation is your total reward over your entire trajectory. Expected total reward over the distribution of trajectories tau induced by the trajectory distribution for parameters theta by running your policy. Make sense?
Basically, kind of put in like intro to advanced track terms, you're trying to train a model, some sort of neural network model. Again, being a little more specific, they're trying to train a neural network model that will maximize the reward that you're going to get if you were to run, like use this model to decide what your agent's going to do in this environment.
Yes. Yeah.
So what happened to the gamma?
Yeah, in general, you would have the gamma T. I just omitted it here for not make it super long. Yeah. But yes, in general, you would have the gamma T right here in the summation. Yeah.
So calculate like expected reward, it's basically going through like all of that. Like
yeah, so in reinforcement learning, if you have, we'll get into this a little bit later, but if you have discrete states and actions, you can actually enumerate all of these and compute this exactly. But typically, In general, we have continuous state and action spaces. So we can't actually enumerate all of them and compute this expectation. Exactly what we do is we take samples. So we roll out our policy and do, it's just taking an average is usually what we do. It's just a Monte Carlo estimation. Yeah.
Are the rewards that you get for like succeeding the task like is it just 0 and 1, or is there like weighted things?
Yeah, so that's a really great question. So it turns out reward engineering is a really difficult problem. And in a lot of settings, humans have to manually write reward functions. So you have to write something like, in the robotic setting, if the sensor sees that, you're successfully gripping the block, whatever you're trying to pick up, then you get 1 reward. And otherwise you get 0 reward in other time steps. There's also other ways you can parameterize the reward function, like maybe you actually get a little bit of reward for getting close to the block, and it's not actually binary, and like maybe your distance to the block is also accounted for in the reward, but it's up to the human designing the reward function to kind of implement that. And those have different implications for how easy it is to train your RL agent. Yes.
So the piece of data tau is the policy applied with some sort of weights data to get the tau for the
Not quite. Yeah. So let me explain this again. So this is tau. What this tilde means here is sample from a distribution. So this expectation notation here means what is the expected value of what's in here, given you're getting trajectories, sample from a distribution, sample from a distribution defined by p theta tau. And what is p theta tau? P theta tau is this. This is your joint probability distribution over all your states and actions, given that you're following a policy pi parameterized by parameters theta.
So your weights.
Your weights.
Yeah.
So in other words, what this is saying is that what is the expected reward you're getting, given that you're running some policy pi, so maybe it's a neural network policy, that has weights theta. And you're just running that policy and you're collecting your states and actions. Make sense?
Yes, that's like run a simulation n times, right? You get sample vectors and you can score
The average, yeah.
And the important thing is in like supervised learning that we talk about in beginner track and advanced track, that p theta of tau is fixed. We have a fixed data set that never changes no matter how we train. But the really important thing with reinforcement learning, why it's like a more generalized version of what we consider supervised learning, is because your distribution is now changing depending on what your model is. Because your model determines how your agent moves, and how your agent moves determines what you see, and thus what your observation is, what the states are, et cetera, et cetera. Which is why reinforcement learning is a more general and more difficult problem than just, machine learning is too gradient descent and stuff like that.
So does that mean the model also changes, or does it, or do we
Yes.
keep the model the same, or
Yeah.
change the?
Yeah, we'll get to that in a little bit, but yes, in general, the model does change during training. So if you think about what's happening in supervised learning, this is a very similar objective. So in supervised learning, you also have this theta star argmax over theta, except you have an expectation over samples from your data set. So xy sampled from your data set. And inside here is your loss. And you're minimizing that, your expected loss. That's the difference. Okay. And as Jordan mentioned, the key differentiator here is this theta term in this distribution. We don't have this theta term here in supervised learning. So every time you change your neural network parameters theta, you're changing your trajectory distribution, which changes this whole thing. Okay. So just to give a more concrete example of what the state action reward spaces look like in the examples I mentioned earlier, for instance, in AlphaGo, a Markov decision process, the state space might be the state of the board, like a 2D grid. You can just represent this by binary matrix. The action space would be like the moves on the Go board, and the reward might be something like 1 if you win, 0 if you lose. And the dynamics, the transition probabilities are given by the rules of the game. Here it's deterministic because you put a piece and it goes there, it doesn't appear somewhere else. In robotic control, your state space might be something like your camera, your sensor readings, your action space is continuous, your motor torques. And your rewards, like I alluded to earlier, there might be many options here. It might be something like 1 if you pick up the object, 0 otherwise. You might have terms that include things like how fast you're able to do it. It might be like your negative time to pick up an object. And the dynamics are given by real world physics. So no simulator here. And then I'll talk about how this is done later with ChatGPT, but your state space would be something like your user input. Your action space would be the large language model output. Your reward might be something like 1 if human likes the response and 0 otherwise. And here, actually, the way they formulate is a little bit surprising, but the way ChatGPT does it is they actually formulate it as a one-step markup decision process. So it actually restarts the environment, even though you're chatting back and forth. The way they do it internally is they treat it as one-time step. Okay. Any questions on the formalism? Anything we've gone over so far before I talk about some algorithms? Okay. So the first thing we're going to talk about is not actually a reinforcement learning algorithm. This is actually completely supervised learning. And this is an algorithm called imitation learning or behavioral cloning. So in this setting, we're trying to solve the reinforcement learning problem using our tools from supervised learning, given some additional assumptions that we don't make in general. So the reason it's called behavioral cloning is because we're trying to clone the behavior of some other agent. So say you're trying to train a self-driving car, and the great thing about training self-driving cars is that there's great, or I guess not every human is great at this, but there's lots of examples of humans that can drive decently well, and you can collect this data. So maybe you take this car, you put some cameras or whatever other sensors on it, and then you ask an expert human driver to drive around, and then you just collect at each time step, what did the sensor see, and then what steering and acceleration did the human put in. You collect this large, supervised data set. And now all you do is you just train with supervised learning some neural network. Maybe it's a CNN, takes in the image, observation, and then outputs the steering and acceleration. That'll be your neural network policy. And you just train it with normal supervised learning. There's no RL in here. And you can learn a mapping from state to optimal action. So sounds like it's good, right? We don't need anything else. But it turns out, does it work? Well, it sort of works and it sort of doesn't. And a really big problem here is distribution shift compounds over time steps. So this is alluding to how changing our parameters data, changes our trajectory distribution. So for instance, suppose we have state on this axis here, we have time on this axis here, and then the z-axis is your reward. So maybe in self-driving, it's like, something about getting to your destination correctly or how fast to get there, whatever it is, doesn't really matter. So maybe, in training, your human data, it looks like this. You're visiting some distribution of states that looks like that. The problem is whenever you're training some neural network, it's not going to be perfect and it's going to make some mistakes. So at the initial state distribution, it's going to be okay. It's going to stick close to the distribution of states you see during training. However, it's going to not be perfect. So it's going to make some mistakes. It's going to do something that the human's not going to do. And it's going to end up in a state that's more different and drifting away from the distribution of states that the human sees. And then every time it does that, it's more and more likely to make a mistake because it becomes more and more out of distribution. So just to give a concrete example here. So maybe you have your self-driving car, it's driving on the road, and then because your neural network is not 100% perfect, it like swerves a little bit, and now it's like slightly, off center of the lane. But now, in your human data set, the humans were never off center of the lane. And so now the neural network doesn't know what to do. It's going to do something random. And then it's going to drift even further away from the distribution that you saw the humans do. So maybe now it's in the ditch on the side of the road. And in your data set, the humans never drove in a ditch, right? So it has no idea what to do. So it's going to make even more, big mistakes and do even more random behavior. And eventually over time, it's going to just completely go, out of distribution and be completely useless policy. So as I mentioned before, the part where the distribution of your data changes with your policy is really important here, right? What states you see is dependent on your neural network parameters. So the data you see changes when your policy changes. This isn't true in supervised learning, typically, because your data set is completely fixed at the beginning. So this approach doesn't work super well unless your expert, human data really covers the space of all possible states, which is really difficult to do in practice for a lot of different applications. Also, a lot of the times, there is no expert to show it how to do things. Like, for instance, if we're trying to do reinforcement learning to control a robot body that looks nothing like a human, we don't have any expert data for how to control that. And it's often difficult to collect that data. And another downside of this is that you can't actually do better than a policy that was used to collect that data. So if you are cloning human behavior, you're not going to get a self-driving car that drives safer, that drives better than humans, because you're just, at best, assuming you have perfect data, you're going to do just as good as humans and no better. So this is not going to suffice for us. Yeah.
I'm just trying to get an intuitive understanding of distribution shift. So is it like because neural network only looks at the immediate step after that, and that might be incorrect over time, that will shift the action space?
Yeah. So you're sort of alluding to it. The key idea here behind this distribution shift is that no function approximator is completely perfect, and it's going to make some mistakes. And every time it makes a mistake, it's going to be more likely to make even bigger mistakes because the data and the observations you see when you make a mistake start to drift slowly away from what the expert has seen in their observations. And so every time that happens and your observations become more and more different from what was seen in your training data, you're more and more likely to make those mistakes. And so you drift off the road, into the ditch. Any other questions? Okay. So now we're going to actually talk about reinforcement learning algorithms that kind of try to deal with this, time dependency and distribution shift. And so a general outline of what most reinforcement learning algorithms look like, there's kind of these 3 steps that might be done in slightly different ways, but this in general is what is happening. First, you generate samples, you run your policy. So usually this is, if you're starting from scratch, you're starting with a randomly initialized neural network, it's going to do something random. And then what you're going to do is that you're going to have all this data for the states and actions that you saw and the rewards you got, and you're going to fit some kind of model that is dependent on the reward that you got. And then you're going to use that to improve your policy somehow. And you're going to repeat that over and over again. Now, the reason we want to repeat this over and over again is for distribution shift, like I mentioned earlier. So, you generate samples here, you do some kind of, neural network training with these 2 steps. And the problem is now your state distribution changes. So in general, you should collect more trajectories because now you're in a different, state space, and you repeat the process over and over again. So the first algorithm we're going to look at is policy gradients. And so what we want to do here is try to use normal gradient descent like in supervised learning, but for the reinforcement learning setting. You might be thinking, we can just, make the rewards negative, and then we just backprop, we treat it as a loss, and we backprop. But it turns out you can't actually do this in general. And the reason is because we can't actually compute the analytic gradient of the reward with respect to the policy parameters, because in general, in the expected total reward term we have here, we have this term P of ST plus 1 given ST AT, or your transition distribution. And in general, we don't have ways to compute the gradient of that. So for instance, if you're running a robot in the real world, you cannot compute the gradient of the real world. We don't have that. If you're doing a simulation, you can write it in a way such that you can backprop through it. But in general, you cannot do that. So we have to figure out a different way of computing the gradient. So instead what we do is compute an approximate gradient of the expected reward using samples, which, as I mentioned before, we collect by running the policy multiple times. Then we compute the gradient of this J term here, J of pi or J of theta. And this is just the definition of expectation here. We're going to compute the gradient of this instead, the expected reward, rather than the negative reward and using it as a loss. Yeah.
So just to clarify, the reason that a normal gradient descent wouldn't work is that there are too many variables in the conflict. That's what putting the rate with respect to some variables doesn't make sense.
Yeah, it's more like, okay, so you have this expectation term we saw before, expected total reward over your trajectory. If you look at what that actually entailed, this is P of tau. We don't have the equation for this term in general, right?
Also, another way to think of this is, for those of you who may show up to workshops open day, you may remember us saying, it's like, oh, for the way you train a neural network model is you want to calculate the gradient, right? And what you would do is you'll say, oh, we have the loss, we have our initial input because the model is something that we created, we know the math behind it, we know how to calculate gradient with just a bunch of chain rule, right? Like, because we know exactly what we're doing to to this, to go from the input to the output, we can calculate the gradients, right? It's just a bunch of matrices. However, imagine you have a robot in real life trying to do this. You have your final reward. So we have our input, which is our observation. It goes through real life, right? This is not a mathematical model. This is real life physics. The robot does something and it gets a reward. How do you pass a gradient through real life? You can't, right? If you have a simulation, you can potentially write it in a way that you take in all the mathematics of that simulation and calculate the gradients, but you can't do that in general, especially with real world robotics, which is why we can't just do gradients. We can't just say, oh, let's just calculate a gradient and just multiply it with learning rate, just subtract it. We can't just do that. We have to do more, which is why we have this whole thing.
Yeah, does that answer your question? Okay.
I know there's some people who are working on trying to imitate gradients in real life with camera stuff. It's wild.
If you're interested in this, there's a team at Google that works on a library called Brax, and basically they make a physics simulator that's fully differentiable. So you can actually do the thing I described here, but there's some really complicated engineering that goes into that, and it's kind of not worth it if I'm being honest. Okay. All right. So now, yeah.
Since you're approximating the gradient based on samples, is overfitting a concern in reinforcement learning?
Yes, it is. Yeah. Yeah, so all the problems with machine learning we have still apply here, and there's more problems, so that's great. Okay, so now we're gonna actually kind of derive the policy gradient in a way that we can use to actually take samples and compute this expectation. Okay, so just bear with me. I think this will be the most complicated math slide, and then after it'll be downhill, hopefully. Okay, so we have, we want our gradient of J here, our total expected reward. And so this is just the definition of what our objective is. So now we're gonna expand the expectation. This is just the definition of expectation. So your integral over your probability distribution times whatever you're taking the expectation of. And now this is just math 32a, I think. You bring the gradient under the integral. And now you do there's a log derivative trick. Okay, so just bear with me. So let's ignore this. Let's just look at grad log p. Okay, so what is grad log p? Grad log p is gradient of p times 1 over p, right? And if you rearrange those terms, it turns out that this is equal to this. It's just chain rule definition of gradient. Gradient of log p is gradient of p times 1 over log p. So therefore, if you rearrange the terms, gradient of p is equal to p times gradient of log p. Yeah, Jordan's got it.
I don't. I do not have this. Wait, so do you multiply with something? Oh, you don't have to read. Right.
Gradient p.
Gradient of p.
Now you rearrange the terms. So now gradient p is equal to this times this.
Yeah. So you have this situation, gradient of log of that. And if you remember, the derivative of a log is 1 over the thing inside, and then the derivative of the thing inside, right? So what you can say is, oh, because we have this really annoying 1 over, let's multiply this over.
Yes.
And suddenly we have the that's why we have the p of t theta outside. And so we have a way to actually write the gradients using a log thing.
Yes. Exactly. Okay. So now we have an integral with this p, tau term. We're gonna turn it back into an expectation. So an expectation is again, it's just an integral or sum of some probability distribution times whatever you're trying to take the expectation of. So this term goes away and becomes an expectation over tau sample from this. So this is the same thing as p theta. I just kind of took it from somewhere with slightly different notation, but this is the same as your probability distribution sample trajectory from running your policy pi. And then you just have the rest of the terms here. So grad log p times your word of your trajectory. Okay. Okay, this last step, just don't freak out. Okay. So, okay. If we recall, you recall, the probability distribution over your trajectory is this term here. So your initial state multiplied for all time steps, your policy times each transition distribution. Okay. I wanted to make this fit on one slide, so that's why there's some stuff skipped here, but it should be okay. So that P theta is here, it's this thing, and that's a bunch of things multiplied together. And a log of a bunch of things multiplied together is a sum over all those things. So it's a sum over all those log terms, log of every single thing multiplied here. Okay. And then we're taking a gradient with respect to theta, and the only terms in here that depend on theta are your policy distribution pi. So all the other terms, your transition probability and your initial state probability goes away. And you're just left with the sum of the gradient of all the logs of your policy pi distribution AT given ST multiplied by the reward of the entire trajectory. Okay, I know that was a lot. Does this make sense or no? Any questions about this?
Well, in fact, this is why when you read machine learning papers, you will see a lot of logs everywhere. You're like, I have no idea where this log comes from. It's because taking derivatives of things multiplied together is really annoying. Product rule, right? It's really, really annoying, especially when we have a lot of things multiplied to each other. But taking the derivatives of things added to each other is really easy. Just take the derivatives of them separately, right? So which is why machine learning scientists love putting logs in front of things, because if you can somehow turn the loss function or the thing we're optimizing into a log, we can just put all these things are being multiplied together and just turn them into sums. And we know we can calculate, the derivative of a log really easily. We have it clearly defined here. So that is why we love logs in machine learning.
Any questions about this? I know it was kind of a lot of math on one slide, but I wanted to not make it multiple slides because that's too much. Okay, so let's take a look at what we have here. So what we have is, if you sample, you run your policy, you collect a bunch of trajectories, we can compute every term here, right? This is all your action distributions. You just take the gradient of that. This is a neural network. We can backprop through that, right? We can compute everything to the left of this so far. And then your reward is given by your environment. So what reward you got when you ran your policy. So we know every term here. And now we have this expectation. This whole thing is a number. And so defined over trajectories. So for all of our trajectories, if you have n trajectories, you just average over them and you compute this term. And then you have your gradient. That's it. Okay, just making sure. Any questions about this? I know this was a lot. Yes.
So where did the P of ST plus 1 given ST and T go?
Yeah, so we're at this step here, we're taking the gradients of that. So because this is that. So because we're taking the gradient with respect to theta, every term in here that doesn't depend on theta goes away.
Oh,
So it's only pi your policy.
okay.
And that's why we only have pi here. We don't have your initial state distribution or your transition probabilities, P of ST plus 1 given AT ST. Any other questions? All right, so just to kind of formalize the entire algorithm, this is called the policy gradient or reinforced algorithm. So what you're going to do is you're going to sample a bunch of trajectories tau by running your policy pi in your environment. Then you're going to compute your gradient of your objective. This is the exact equation that we used on the previous slide, except kind of broken down in the setting where you're taking multiple samples. It's the exact same equation. And then you just do gradient ascent because you're trying to maximize your reward and update your parameters data. Then you repeat it over again until you get your desired performance. Okay, some things to note here. Well, first thing is that you must collect new data every time you take a gradient step. Why? Because when you change your theta parameters, this equation changes. So all the data you collected previously from your previous trajectories is no longer valid because your new policy will visit new states, which will receive different rewards. So it will be no longer valid. And that means every time you take a gradient step, you need to collect data again. So you can see how this is getting very annoying compared to supervised learning, because every time you change your neural network, now you need to collect an entirely new data set, which is different. And then you have to repeat the process again. Another thing is that going back to the diagram I had before, so we have the generate sample step and the fit a model to estimate return. Here we're just looking at the sum of total rewards. And then to improve the policy, we're computing a term that's a function of the rewards we got in our trajectory, and then taking gradient ascent steps for that. And a more advanced version of this actual algorithm called policy proximal optimization is what is used to train ChatGPT. Any questions here about the practically running this algorithm? So let's take a step back and look at some intuition and compare this with what we're doing with supervised learning or behavior cloning in the RL environment context. So up here we have this equation for the policy gradient, exact same equation found on the previous slide. And then we have our maximum likelihood. This is supervised learning objective. So we take n samples. Our gradient is defined over n samples over the log probability. This is just a neural network if you're just trying to predict the action. And what you'll see is that these equations look very similar. They're basically exactly the same. The only difference here is that with a policy gradient, we're multiplying by the total sum of rewards. So what's the intuition here? What we're doing in supervised learning or behavior cloning is that we're trying to maximize the likelihood of the data we see collected from our experts. So we're just saying, the human took this action in the state. We're going to make our neural network predict that more and more often. We're going to make that action more likely. With policy gradient, we have a term here for making that action more likely, but it's scaled by a reward, how good it is. So if it got really high reward, we're going to make that action a lot more likely than an action we saw in our data set that got very low reward. Notice that in supervised learning and behavior cloning, there was no reward term at all. We just assumed that everything the human or expert did was optimal. We're just going to make all of those equally more likely. In policy gradient, we say we make the actions more likely in proportion to how much reward they got. So just to kind of visualize this a little bit more, again, we have state on this axis, we have time on this axis, and Z is our reward. This red area here is an area we got high reward. We're going to push the probability mass of taking actions and going to those states up. Whereas in supervised learning, we just see if all three of these were seen as trajectories, we push them up equally. With policy gradient, we push up the one with the most reward, the most. This is how we formalize mathematically how we do trial and error in reinforcement learning. Yeah.
I'm not sure if I grasp how the equation that you derived the policy gradient earlier lends itself to this visualization that what answer.
Sure. So say our n here is 3. We have 3 trajectories that we sampled. The 3 trajectories look like this, and this color heat map tells us how much reward we got for each of those trajectories. This is what our gradients look like for policy gradients and for maximum likelihood, which is supervised learning, right? Think about what's happening here for each of these time steps where we're taking an action. In policy gradients, the actions in this trajectory here in the red will have the largest gradients, whereas the trajectories for these will have less gradients in proportion to how much less reward they got. Any other questions about this intuition? Okay, should we take a break?
Yeah, a quick 2 to 3 minute break and use the bathroom, and we'll come back to more of this.
Yeah, we'll come back at do 5 minutes. We'll come back at 1:03.
Yeah.
Okay, let's get started again. Okay. Yeah, I guess I'll go over this. Okay. What the? So there's another class of algorithms in reinforcement learning, which are value-based methods. So we're going to introduce some objects here. We're not going to go over them in super big detail, just for time's sake. So you can define something called a state value function, or V5S, and this is your total expected reward given that you start in state ST. If you run policy 5 for the remaining of time, your total reward you get to the end of the trajectory, given you start in state S at time step T. And there's also a state action value function you can learn, which is a function of your current state and action, which just defines your total expected reward if you're in state S and you take action A. So the total reward you get for the rest of your trajectory. You don't have to worry too much about these expectations. Just know Q of SA is you're in state S at some random time step, doesn't matter. If you take action A, what is the total expected reward you're going to get for the rest of your trajectory? V is the same thing, except it doesn't take A as an input. So there's a concept called the Bellman optimality equation, which defines some constraints on what the Q function looks like for your optimal policy, so the policy that maximizes the reward. And the constraint is that the expected reward you get from taking action A at time step S, or the total reward you get, the Q value has to be equal to the reward you get at the immediate time step, plus the discounted reward over the action that maximizes your Q function for the remaining time. So this is a recursive constraint that must be true for the optimal policy. So let's think about why this must be true. So your policy is optimal, right? So Q tells you how much reward you're going to get for the rest of your trajectory if you take action A in state S. If you have an optimal policy, this value must be equivalent to the reward you get immediately plus the action that would maximize your Q value at the next time step. So this must be true if you have a Q function for your optimal policy pi star. And so what you can do is a little bit of a hack. This isn't perfectly correct, to be honest, as a lot of things in deep learning are. You can set the thing inside this expectation to be some value. We'll just call it y. And then you can define a loss to be just a mean squared error between y and your Q function. And then what you do is that you have some policy and then you collect trajectories. And this gives you everything you need to compute this. And then you just pretend that it's linear regression and you just train a neural network and it somehow works. So this is called Q learning. This algorithm is as follows. It's also called fitted Q iteration. What you do is you collect a data set of trajectories, and from that data set of trajectories, you can collect these 4 tuples that consist of a state, action, next state, and reward. Then you use that to compute y, which you then use to compute this regression loss, and then you just update your neural network with gradient descent. So this is what's used in DQN, the first DeepMind paper that solved Atari at superhuman performance. Notice that there's a lot of restrictions with this algorithm. First of all, it's not theoretically very sound, so it's a little unstable, but it sort of works in practice, so people do use it. The second thing is we're pretending, so y here is actually a function of your Q, your neural network. In general, linear regression, your y, your target values are not dependent on your neural network, but we're going to ignore that and actually not backpropagate through that, even though technically, if you're computing the gradient, you should be doing that. Yeah, it's not great. And another thing about this is that there is a benefit to an algorithm like this, which is that it's off policy, which means that you can actually use data from any policy that you want. And if you have a Q function, when you do this, hopefully what's going to happen is that you have a Q function or neural network that exactly satisfies this constraint because you're trying to regress to it. And if you do, that means you have the Q function of the optimal policy, but that's not a policy in and of itself. So if you want to recover a policy from your Q function, what you do is you act greedily with respect to that Q function. So whenever you're in state S, what you do is you pick as your policy your action that maximizes Q. So I'm in a state, I see some image, I plug in every action I could possibly take into my Q function, and I decide to do the action that has the highest Q value. And assuming that your Q function satisfies the constraint on the previous slide, it must be the Q value of the optimal policy, and therefore you will be executing the optimal policy. I don't like this algorithm very much, but it works. It works in settings. Also, note that because when you're doing inference, you have to do this max over your actions. You can only do discrete action spaces. Because if you had continuous action spaces, you can't enumerate, you can't compute an argmax over this. Or you can if you just discretize the space, but it's not very good for that. Yeah.
Is it just like policy gradient, but you do the gradient descent multiple times?
No, not quite. Because here you're not learning a policy. Your policy isn't even a neural network. You're learning the Q function, which is a function of a policy. And then you're just like running these gradient updates to force the Q value to be close to satisfy constraints that the Q function of the optimal policy would have, and then you act greedily with respect to it to recover a policy.
Interesting.
But I don't like this. It's not very good.
So what exactly is a Q function? Like in when we're applying this to real life stuff.
So your Q function, like I said before, just tells you it's a function of state and action. If you're in state S and take action A and execute policy pi, what is the total expected reward you should get from that time step forward to the end of time? Okay. Any questions about Q learning? There's also model-based RL, which, not to be confused with deep learning model, it's not very good terminology, but a model in this context refers to a model for the dynamics. So sometimes actually you do know P of ST plus 1 given STAT, or you can learn it with a neural network. So if you collect trajectory data, you could theoretically learn a network that takes an STAT and outputs ST plus 1. And then you can use this in order to do some algorithms that make use of that. You can compute that analytically. We're not going to really go into depth here because it gets really complicated, but just know that it exists. And there are methods that utilize this information. Okay. And probably the most famous example of model-based RL, this is coming from the Google Brain team, is called Dreamer. So basically they, learn a model of the world that predicts the next state or next observation given the previous state in action, and they can do some fancy stuff to kind of back propagate through all of that and improve the model. I'm not going to go into super detail here, it gets a little complicated, but just know that it is a method. And the advantage for model-based RL, at least in theory, is sample efficiency. If you kind of can make use of this additional information, you know how the world is going to unfold. You can, in theory, learn quicker with less trajectories. However, this is in theory because you also have to spend time learning the actual dynamics model itself, which adds training time. So it's not exactly more sample efficient necessarily. Yeah.
Would this not run into the same problem that if there's a small deviation, then that deviation would populate through having that more and more?
Yes.
So that's the same. This would also have that.
Yes. So yeah, that's a great point. So in a lot of these model-based algorithms, what they can do is they can simulate multiple time steps in the future, what the state of the world will look like, and then compute the reward and backtrack from that to try to compute what's the optimal thing to do. And you have that exact distribution shift problem where if your learned dynamics model is not accurate, every time you make a mistake, you're more likely to make more and more mistakes. And so in the future, as you increase the number of time steps you look in the future with your dynamics model, it's could be potentially very off. So that's why very often, typically, either you don't actually plan that far into the future, or you have to recompute over and over again at regular intervals. You're planning into the next stages because you can't rely on your dynamics model being that accurate into the future. so now we're going to talk about some more advanced algorithms here. The core technical stuff is mostly over, I think. This is going to be a little more high level. So just to kind of backtrack and take a bigger perspective of machine learning in general, there's been this emerging paradigm of foundation models, which is right now the dominant supervised learning paradigm. And so what you do is you train a very large model on lots of data, often in an unsupervised way. And then when you want to fine tune it for some downstream tasks, you then take the foundation model and its pre-trained weights, and then you fine tune it with a small amount of data to do well on that task. So for instance, in NLP, you might just take an off-the-shelf llama model or GPT model from OpenAI or Meta, and then you will fine tune it on your downstream NLP tasks with the specific data set you have for your particular application domain, and that tends to work pretty well. It's better than training a model from scratch on just a little bit of data. And so one emerging paradigm is we want to be able to use foundation models for reinforcement learning problems. And most of the recent foundation models have all been transformer-based. So things like GPT, Llama, Vision Transformer. And so this is actually a work that came out of my current master's advisor. One of the authors on this paper was Decision Transformer. It's basically you apply GPT for offline reinforcement learning, and you're basically treating a trajectory like a language. So each token or each word in the language is a state, an action, and a reward. And you can actually, it turns out you can model trajectories pretty well that way, and you can learn policies. So, if you have a current, state and action, you can condition on reward to go, the reward that you want to get. And it actually turns out you can recover a policy from this, and it does decently well. And a lot of the current state-of-the-art robotics RL models are also transformer-based, very similar to this as well. So yeah, I'm going to skip over this. It's pretty competitive with other offline RL methods. This is actually a little bit outdated now, but there's some work coming out of DeepMind where it turns out you can actually learn a bazillion different tasks. This is just decision transformer on steroids. And it turns out you can do a lot of these really interesting tasks really well with a single model, which is pretty impressive, unprecedented before using transformers. Okay. Are there any questions about any of the RL algorithms we went over? Yeah.
For language, what would it mean to have a policy?
I'll get to that in the later part. Yeah.
Yeah, if we refresh the slides, I added a thing at the end.
Okay.
Yeah.
Okay. So now we're going to talk about how reinforcement learning is currently being deployed in various application domains, including ChatGPT. So yeah, that's where we're going to start off with. So ChatGPT has a very, honestly, pretty complicated multi-step training process. So there's three big steps we can think about here. Actually, I would say there's four. So there's one that actually happens before this, and this is pre-training for GPT. So for those of you who are unaware, ChatGPT is based on GPT, which is generative pre-trained transformer. This is a neural network that is trained to predict the next token. So what they do is they scrape all of the internet, they take all of the text that humans have ever written on the internet as much as possible, and then they feed it to a transformer. And what does this transformer ask to do? It says, given the previous pieces of text, what's the next token? What's the next word going to be? And it does that for all of the text on the internet. And it turns out, if you do that with enough data, with a large enough model, it actually learns to do this task pretty well. And there's a lot of emergent capabilities that come from this kind of pre-training process. And it kind of is able to really reason and understand language really well. However, this isn't perfect. And this isn't perfect for things like chat and dialogue applications. And the reason is because it's not very good at following instructions. The distribution of things that humans ask a chatbot to do is very different from the distribution of text you see on the internet. If you ask ChatGPT to make a recipe for sandwich for you, you probably don't want it to try to regurgitate what the most likely Reddit user would say. That's probably not what you want. So you want something a little bit more intelligent. So there's three additional steps. There's three additional steps that are added on top of this pre-training process that actually makes it useful for following instructions and doing dialogue. Okay. So the first step is what's called instruction tuning or supervised fine tuning. And so this is when you ask a bunch of humans to hand curate a list of instructions, and also another separate set of humans to hand curate a set of responses for those questions. Because what we know is that these, models are going to be mostly used for instruction following. So we need to fine tune our model to be more domain specific for instruction following. So we do that with just normal supervised learning, exactly how you would expect, given the instruction, predict the correct response. That's step one. This is SFT, supervised fine tuning. The second and third steps are really where the reinforcement learning comes into play. So the second step, we'll go into all these three steps in a little more detail, but in general, what we do is we train a separate neural network that learns human preferences. This is our reward model, and it's going to, given some text and a large language model response, output some scalar that is somewhat representative of how good a human thinks this response is, and we're going to use this as a reward function. And then finally, in step 3, we're going to use a reinforcement learning algorithm, in this case, policy proximal optimization, which, as I mentioned earlier, is a more advanced version of policy gradients or reinforced, which we went over earlier, in order to optimize the language model to produce responses that maximize the reward that it gets. And as I mentioned before, the reward is defined by the neural networks trained in step 2. So go into more depth into all 3 of these steps. But before we do that, we should introduce a paradigm. This paradigm I just described on the previous slide, step 2 and 3, are what's called reinforcement learning from human feedback. So as I alluded to earlier, it actually turns out in many cases, it's really hard for humans to hand define and code up a reward function that actually defines what we want. And most real world environments do not have obvious reward functions. So this is a work actually from 2017 for OpenAI, where what they do is that they don't even write a reward function. They just say the reward function is this neural network. And they train this neural network to produce a reward scalar that predicts, whether or not a human thinks this is close to backflip or not. So they're trying to get this robot to perform backflip in simulation. And it turns out it's really difficult to hand engineer a piece of code that says, yes, this robot completely, did a, I need to charge my laptop. It's really hard to write a function that says, that is 1 if the robot did a backflip and 0 if not. Like, just imagine what that would be like. That's actually pretty difficult. And so what they do is they ask humans to label whether the left or the right video is closer to a backflip, and they use that to train a neural network so that it can do that itself. So here you see the process of what human annotation looks like. They're just selecting which one looks better. And then eventually over time, this trains the reward model, which is then used with a reinforcement learning algorithm to train the agent and the policy to maximize the reward outputted by this reward model neural network. And eventually it's able to do the backflip pretty well. So this is in essence what we're doing, but now for language models as our policy. And so just to give you an idea of how effective this method is, the work that actually pioneered this method before ChatGPT was released was called InstructGPT. And what they do, what you're seeing here is on the y-axis a Likert score. So what they do is they, given an instruction, provide 2 large language model responses from 2 different large language models, and they ask human annotators. This is absolute scale. So sorry, they give a single large language model response, and then they ask the humans to rate it from 1 to 7, based on like how good they think it is. And the really important thing here is on the y-axis here, this is how many parameters the GPT model has: 1.5 billion, 6 billion, 175 billion parameters. The line in blue is the GPT model trained with reinforcement learning from human feedback. And the 6 billion parameter model trained with reinforcement learning from human feedback beats every single other model, even the 175 billion parameter models not trained with reinforcement learning from human feedback. As we all know, scale of data and parameter size typically increases performance pretty drastically for neural networks. But the fact that the 6 billion parameter model with like more than 10 times less parameters than the 175 billion parameter model is better with reinforcement learning from human feedback is a pretty good testament to the efficacy of this particular method. So let's take a deeper look into the 3 steps that I talked about. You have a question? Yeah.
For the instruction PC, I don't know if I'm looking at it wrong, but from 1.5 billion power to 6 billion, why would the score go down?
Yeah, that's probably an artifact of the training process. It turns out that RLHF is pretty unstable to train. And so, yeah, you would expect it to be better, but this might have been just some weird training artifact that I'm sure they've probably fixed at this point. Yeah, there's a lot of weird things with deep learning like that. Yeah. Also, it might just be annotator noise as well, because people rate things very differently. Okay, so step 1, this doesn't involve RL. This is just supervised fine-tuning. So this is an example of the data sets that they use to do supervised fine-tuning. So for instance, it might be like a multiple choice question or some other kind of logical reasoning questions. And the input is going to be fed into the transformer, and it will be tasked with predicting the next tokens. With normal supervised learning will just be the outputs here. Very simple, just normal supervised learning. All of these instructions are written by humans, and all the responses are written by humans, and we just ask the model to predict those correctly. Now to the RL stages. There's step 2 here, which is learning a reward model. And so what happens here is that we take a language model and we ask it to perform some task, like some instruction. Then what you do is you sample it multiple times. Say you get these 4 responses, A, B, C, and D, all sampled from the same model. You then ask a human labeler to rank the outputs from best to worst. And finally, what you do is you take that preference data and you train a separate, completely separate neural network that takes in both the instruction and one single response, and then outputs the probability that that response won a random competition against another response. So just to put things into more concrete terms, here, D is rated better than every other response. So if you paired it against any other response, the probability that it won that comparison is 100%. So if you feed this instruction and response D into this neural network, it should produce 1.0. If you take answer C here, if you paired it against every other response, would win 2 out of 3 times because it's better than A and B and worse than D. So if you feed the instruction and answer C into the neural network, you should output 0.66, and so on and so forth for every response. So this gives us a separate neural network, which takes in some input to a large language model, some output to a large language model, and outputs a single number scalar, which tells us how good a human would think this is. And then we use that in step 3. We use that as our reward function to optimize our large language model with reinforcement learning, some policy gradient algorithm. In this formulation, the states are the inputs, like the instructions. The actions are the text outputs in the large language model. And the reward here is the output from the reward model if you input into the reward model the instruction and the action taken by the large language model policy. And as I mentioned before, ChatGPT is trained using PPO, which is a more advanced version of policy gradients. And the key thing to note here, and why this method is so effective and scalable, is that you only need a data set of prompts containing instructions. You do not need humans to write the correct response to what the instruction will be, unlike in the first stage. And this lets you use a lot of data. It lets you use data where you don't already have human labelers, which is expensive to acquire, because you get feedback in the form of the reward score, which is defined on the output the language model provides given some instruction. Okay. Yes. Yes. Yes, you do need humans to train the reward model. But you do that one time, hopefully, and now you can use as many prompts as you want and get, train on that. Any other questions about these 3 steps? Okay. So you might ask, as many of you might be wondering, why reinforcement learning for language models? Why shouldn't we just keep collecting more supervised data, just collect more instructions, ask more human responses, and then just do supervised fine-tuning? So beyond what I just mentioned, where you can scale up the amount of data you use by just using a data set of just prompts, there's other reasons why you might want to consider reinforcement learning. The first is negative feedback. If you think about what you're doing with supervised learning inside of language models, what you're saying is that here's a data set of a bunch of text, a sequence of tokens, inputs and outputs. Make everything in that data set equally more likely. This is the equivalent of behavioral cloning for language models. However, when you're using something like a reward model and policy gradient algorithm, you can actually have negative feedback. You can say, this thing is really bad, like harmful outputs, racist, sexist, misogynistic outputs, and give a really low reward, because hopefully your human annotators will say that's bad. Not necessarily a given, so you gotta be careful about that. And you can say, this is low reward, and so in policy gradient, we're gonna make it less likely to happen. You can't do that with supervised learning. Another thing is distribution mismatch. So if we didn't have these 3 steps at all, like I said before, you don't want, a sandwich recipe from the average Reddit user. You want something that's a little more similar to what you actually want. So you want the input distributions to be more close to things like instructions, which is what you actually use a chatbot for. Another thing is diversity. Many responses have many valid outputs for some given prompt or instruction. And you can, hopefully, if you train your reward model well, you can have this reward model generalize and output similar rewards to all of those outputs. And one of the last reasons you might want to do reinforcement learning from feedback is reducing hallucination. So for those of you who are unfamiliar, hallucination is a phenomenon where language models just confidently make up facts and output them as if they were true. And one intuition why this might be a problem in pre-training is that the pre-training objective encourages the model to lie. You cannot express uncertainty in knowledge because those kinds of outputs have really low likelihood. Like just go on any Reddit forum and see how the users talk, right? There's no, there's not that much nuance and people are very confident in exactly what they're saying. And if you're trying to mimic that kind of style of writing, even if you know something is false, if you're mimicking how humans interact and talk on the internet, you're gonna want to sound confident and sound like you know exactly what you're talking about all the time, which is obviously not a good thing. So with reinforcement learning from human feedback, if you train your reward model with the correct data, you can penalize making confidence statements when there's a lot of internal knowledge uncertainty inside the model. And just to give some empirical evidence for this being successful, these are a couple of the really largest models out there today. Anthropic is a competitor to OpenAI. So if you take their base LM and you compare it against their RLHF language model, this is a benchmark that measures accuracy, truthfulness on some multiple choice questions, I believe. RLHF has a clear advantage here. Same thing with GPT 3.5. GPT 3.5 Turbo is ChatGPT, the original version. And then GPT-4, base, U-shot learning, RLHF does better by a large margin. So it is effective in reducing hallucinations and improving accuracy and truthfulness in large language models. Obviously, it doesn't solve everything. We've seen all those news stories of people using ChatGPT and thinking it's like Google search. And obviously that's still a problem and it's not 100% fixed, but it's definitely a lot better than it otherwise would be. Yeah.
You mentioned that some of the meta hallucinations is very confident and it has internal knowledge and certainty. Is there a way to measure internal certainty?
Yes, there is. I don't want to get into it now, but if you are interested, you can look up. There's a paper called Language Models Mostly Know What They Don't Know, I think, or something. It's from Anthropic or OpenAI, and they provide some methods for investigating that. Okay. Some other perspective here. You might be wondering why ChatGPT is free, considering it costs a lot, like hundreds of millions of dollars to train and do inference. It's the fastest app ever to reach over 100 million users, I think in like a couple of weeks. The basic just is they're collecting your prompts, basically, what you give it to the model to very likely add to their prompt data sets so they can get data that's more in distribution to what users have. And they also they haven't said this publicly, but it's very, very, very likely that every time you do something like click stop generating or regenerate response or thumbs up or thumbs down, you're effectively giving them preference data they can use to train better reward models. And they can use that to improve their models, especially with the very large scale that they've reached. They collect a lot of data and they improve their model from that. Yeah.
This could be just totally off the mark here, but with like, rather than taking like specific reward inputs, could you have like some sort of like reward processing in and of itself? So if someone says like, thank you, chatbot, it takes that as a response to the feedback.
Yeah.
I would assume I assume they do something like that as well.
Yeah, there's been a lot of recent works on using more fine-grained feedback in the form of text. Yeah. Yeah. So I'm sure they're working on it internally. They're not very public about a lot of this stuff. So yeah. Okay. So we'll just conclude with a few other examples of reinforcement learning being deployed in the real world. This is a company, Wave, based in the UK. They use reinforcement learning for learning self-driving. So for those of you unfamiliar, most of the top, self-driving car companies today, especially based in the US, like Cruise, Waymo, Emotional, they do use a lot of machine learning, but they typically break it up into a bunch of different pipelines. So there's a neural network that does object detection, a neural network that takes what the objects they detect and then predicts, where all the cars are going to go. And then they're going to take the output from all those predictions and then put into a separate machine learning model that says, I'm going to plan these trajectories. So there's a bunch of different neural networks chained together. This company is newer and is trying to do something different where they try to basically with one neural network end-to-end learn just a mapping from sensors, images, and pixels directly to steering acceleration controls, which is really difficult. But they have some interesting demos. This is a very early stage experiment. I'll show some more recent work soon, but they're able to somewhat successfully drive on this kind of private road pretty quickly, just with a couple examples. The human, intervenes and provides some feedback, and eventually you'll be able to drive. Let's give it a little bit. Let's try. Here we can see the reward is like the distance to travel. Policy is just some CNN. I believe so, yeah. And eventually able to do it. 11 training episodes, which is pretty impressive. Obviously, that's not the real world, but this was many years ago. Okay, so now a more recent example of the progress they've made. This is just this past year. They're driving on real roads in the UK and generalizing to different cities that they haven't trained on before, which is pretty impressive. And a lot of pretty challenging scenarios as well. Another thing to mention is that all the US-based self-driving car companies, the top ones, they typically require what are called HD maps. So before they drive in any area, you have to go in and at a centimeter level precision, take LiDARs and map out every 3D object. This does not use that. That's why things like Waymo and Cruise vehicles are geo-fenced to areas. They have to 3D map them in high precision before driving them.
Construction. New things being built, things being moved.
Yeah, so there's there's a long tail of data that you have to account for, and that's why it takes so long. Even if you drive well 99% of the time, the really hard part is the long tail, really, edge cases that you really have to collect a lot of data for. Yeah, overtaking a vehicle in a lane looks pretty smooth. Let's move on. So yeah, those are some real world applications for reinforcement learning. And now I'll just finally conclude with some open challenges and future work in reinforcement learning. So one challenge in RL is robustness. So for one, RL algorithms are very sample inefficient and require a lot more samples than humans would typically require to perform a similar task. So robot learning to pick out various objects, it takes like millions and millions of like images and hundreds of thousands of trajectories to be able to do that successfully. Humans typically, babies can learn that pretty quickly, although we have the advantage that we've had, millions of years of evolution, pre-training in our brains, basically. So maybe not the fairest comparison. But ideally, we'd like them to be able to reach human levels of performance in terms of learning speed. Another problem is that they're not very robust. So it's kind of funny. This is like a graph here. This is a half cheetah task. So this is a simulated robot that's like a cheetah. And if you run the same TRPO algorithm, it's a policy gradient based algorithm with 5 different random seeds, if you manipulate the results carefully, you can actually produce results that are outside of a 95% confidence interval from each other. Completely different results statistically. Like your p-values here would be like 0.0016, which is very small, and you can report that as a significant, improvement to your algorithm by tuning the random seed. Obviously, you should not be able to do this. Your random seed should not affect your performance that much, but unfortunately, a lot of these algorithms are very unstable still. We're still, actively we're trying to fix this. Yeah. Yeah. Yeah, so here robustness means the performance of the algorithm should not change due to spurious hyperparameters that should not matter. Like when you change your random seed, when you change how your neural network is initialized, you should not get results that are completely different from each other from different runs and different random seeds. Yeah. Important to mention, we don't see this in supervised learning. If you run the same hyperparameters with different random seeds, you generally get pretty close, same loss performance most of the time. And one big reason of this, as I mentioned before, is data set instability. Throughout the entire process of training, your data set's constantly changing. And you don't have this instability in supervised learning, which makes it a lot easier to have stable learning. Is there a question there?
Oh, yeah. I was just thinking, the future data depends on the back to randomly initialized. And how are there ways to increase the robustness without to have things depend so much like everything depends on the data and
yeah, there's a lot of methods that try to decrease the variance of methods like policy gradient. I can't really get into them right now, but we can talk about it offline if you like. But there's a lot of work. It's not a completely solved problem. Yeah. Another challenge, as I alluded to earlier, is reward specification. Like I mentioned, it's often really difficult for humans to actually write down in code or even in writing what exactly we want from our AI systems. So just to give an example here, there's this video game where the goal is to race this boat and you're just trying to, it's like Mario Kart, but for boats, right? But you also get these intermediate rewards for collecting these little coin thingies. And so what these researchers found from OpenAI is that if you train a RL agent to do this, it will just try to collect these coins in a loop, and it found a way to exploit the game instead of actually completing the race. So you can see here, it's like driving around, and then now it's going to, just give it a little bit, it's going to find a glitch, and it's just going to collect these green little coin thingies, which gives you a reward, instead of actually completing the race, and it's just going to do that in a loop over and over again. And this is an artifact of the fact that you're assigning intermediate rewards to this task, but that's not the actual task you care about. You want to finish the race, right? So the algorithms are very sensitive to how you define these reward functions, and it just gets stuck there. Yeah. So some future work has to really look into aligning reward models with our actual values. What we actually want to happen is not always easy to specify. Okay. One last challenge here is exploration. So usually there's some trade-off between exploring new behaviors and exploiting already learned behaviors, right? So, you have to take some risks and venture into some states. This is just a life lesson in general, right? To actually figure out how you can, achieve better success, become happier. You have to be able to try new things and see what works and what doesn't. And there's algorithms for basically trying to improve how these RL algorithms explore different new states. A lot of them do things like, oh, if you see something new, let's give you some additional intrinsic reward to reward you for seeing something new. However, it's not that simple. So for instance, here's an algorithm where they added an additional reward for exploring states that the agent hasn't seen before. However, if you just add a TV that changes channels really quickly in your environment, just like with college students that look at TikTok, we get really distracted by that because we're getting all these additional rewards and intermediate rewards for looking at something new and novel, and it just gets stuck there and just watches TV all day. So that's not great. That's not actually exploring new behaviors that we want. And so there's a lot of additional future work that's needed to kind of improve this and formulate better ways to explore maybe state spaces that are meaningful for improving things we actually care about. Yeah. So yeah, all the references are here. I think that's pretty much it. Yeah, I'll take any questions, discussion you have. Thanks.
Before we go, a little preview. Next week, we have Pratik and Ovid will be presenting their research that I've been doing for a little bit, which is climate diffusion, using generative models to predict the weather. So if you're interested in that, next week, same time, same place. I hope to see you there.
Yeah, I'll take any questions anybody has, discussion, criticisms, whatever. Yeah.
You would summarize everything in 3 main sentences.
That's kind of difficult. I think, okay, one sentence would be, we should care about making algorithms and making progress on what we actually care about. So this means sequential decision making. This means reward specification. So aligning our, AI, the objectives that our AIs try to optimize is really important. I think the second thing is that, what do you want? I'll do 3 points that may or may not be one sentence. I guess the second point would probably be that RL has shown a lot of success, but there's still a lot more work to be done in all sorts of different problems. And I guess the third would just be data and scale matter in RL in the same way that it matters in supervised learning. So scaling up the data you have for reward modeling and the number of parameters for your models does improve things. It does improve things in things like decision transformers. So the scaling that we see in supervised learning working really well is also really important in RL. So I think maybe those are 3 big takeaways. Yeah. Any other questions? Yeah.
Where do you think RL is going in the future? Are people going to just keep go like the same they did with supervised learning, just keep going deeper and deeper and deeper with more complex models, or do you think they may go somewhere else?
Eventually, I think we'll start using much larger models. Actually, right now, the robotics models we have are pretty small in comparison to the language models we have now. So like, I think the largest like transformers used in RL are only like 20-ish billion parameters. And now we have like trillion or 20 billion. Now we have like 20 or not 20, like 2 trillion parameter language models, right? So like, yeah. Yeah, so I think eventually we'll see that. I think we just need to solve, when you scale parameters, you also need to scale data and algorithm learning efficiency as well. And we need to see kind of that stuff catch up. I think we also need to see our robotics hardware is not very good compared to what humans have. Like, even if you had a perfect controller, perfect RL algorithm policy for controlling a like robotic hand, like we don't have robots that can like do this, right? Like the hardware is just like not there yet. We also don't have the control either, but like there's many other limiting factors for a lot of RL applications right now beyond just the algorithms themselves. So yeah, I would say, yeah, we're definitely going to still see it. It's not going anywhere. Like it's very useful for ChatGPT. It's arguably the thing that makes it not unusable. So we're gonna keep seeing it and seeing it in all sorts of different domains. Yeah.
It seems that human solution is like very useful and very now. How realistic is it just cutting out the middleman? Is it viable or is it a pipe dream?
No, it's not a pipe dream. So if you look at recent works from a company called Anthropic, which is founded by people who left OpenAI, making models like Claude, they use a similar formalism to RLHF, which is RLAIF, which is reinforcement learning from AI feedback. It's also known as constitutional AI. And so what they do is instead of asking humans to like rank responses, you can actually ask an AI, does this response follow or violate any things in the constitution that maybe is written by humans, like don't be racist or like harmful or whatever. And it turns out this works decently well. And the reason is because in general, evaluation is easier than generation. So in other words, it's a lot easier for models to evaluate whether a response is good or bad or racist or not racist than it is for them to generate one that is not racist or good. Yes.
So for these AI models that would be doing evaluations, are they rule-based or are they also neural networks that are like what's the difference?
What do you mean the language models we're using for
Like
evaluation?
for like what I thought is doing, like where you use AI generated feedback into the computer generated feedback, like the AI are giving that feedback. Are they working off like a set of rules and then depending their rules or
yeah, so the rules are written by humans, and then the prompts will be like, here's a constitution, here's a response from an LM, and evaluate it based on this constitution. Yeah. Any other questions? Okay, great. Thanks for coming, y'all. See you next time.